Bismillahirrahmanirrahim. So today we will start with our first lecture, and the course code is PHY 4821. Uh, Name of this course is Engineering Materials, and this one is a two-credit course. So in the screen, I think all of you can see uh, these are the syllabus for this course. So first topic will be the classical theory of electrical and thermal conduction. So let us start with this topic. So for this topic, I would like to follow the book named Principle of Electronic Materials and Devices, written by Kasab. I have already uploaded this book in your Google Classroom, and I also requested you to go through the chapter one. So today we'll start with the chapter two, and you look. The title of this chapter is Electrical and Thermal Conduction in Solids. Okay, so I also request you to go through the chapter one, and in the very first chapter you will learn about the basic properties of materials. That means the face centered cube or body centered cube, what is called crystal, what is called lattice, these sort of things. And I assume that you have learned these sort of things in your university physics 1 and also in physics 2, as because this one is the fourth year course or the your final semester course. So usually I assume that you know the very fundamental things of physics, and I will try to explain something in depth of physics. So I will not go to that much of fundamental things, but if you have any problem regarding the fundamental things, you can ask me these things in the problem solving class. Okay, so usually I try to follow uh, the topic wise. That means I will try to cover up only those topics which is also included in our syllabus. Okay, so let us start the class. So first of all, you will find that uh, the first one is what is called electrical conductions. So electrical conduction involves the motion of charges in a material under the influence of an electric field. So that means if we have an electric field like this, and if we have some electron or if we have some charges there, then if we apply the electric field, then these charges or these electron will experience as a force. These electrons will experience a force, and that one is sometimes we call that one is that conduction electrons or something like this. Now a material is generally called classified as a conductor. Those materials will be called conductor if it contains a large number of free or mobile charge carrier. That means a material is only to be called as a conductor if it contains a large number of free or mobile charge carrier. Is that okay? Now we know that in metal there are usually the metallic bond, and usually there are a lot of number of free electrons are there. So usually these free electrons are called the conduction electron. Okay, usually the free electrons in the metal is known as conduction electron. Now, so in presence of an electric field, the conduction electron attains an average velocity, and this velocity is known as drift velocity. So look, so whenever we have an electric field, in presence of an electric field, these conduction electrons, that means the outermost shell electrons, attains an average velocity, which one is known as drift velocity. That means if you look at the top of this figure, if we have these sort of electrons, then these electrons will collide each other, and that one will move from one place to another place, and that will experience the velocity, and this velocity is known as drift velocity. And the last one, you look, this velocity depends on the field. So if we have a strong electric field, then this velocity will be higher. If we have weak electric field, then this velocity will be lower. I think this one is clear. Now, the another fundamental thing is that good electrical conductor, such as metal, is also known to be good thermal conductor. So, those materials, which one is a very good electrical conductor, that one should be also a good thermal conductor. And the thing is that there are a lot of inner relationship between the electrical and thermal conductivities, which can be supported by also not only by the theories but also the experiments. Now, this one is a very introduction part of our class. That means the electrical conductions, which one is called electron, which one is known as drift velocity, which one is known as conductor, these sort of things. Now, we will go to our first topic. So, if you look the article number 2.1, the classical theory of Drude model, right? So, we will start with the classical theory of Drude model. So, article number 2.1. Now, look, if the electric current density is defined by J, and that can be defined as the net amount of charge flows across per unit area per unit time. That means if we consider that one as an electric conductor, if we consider that one as an electric conductor, and the electric charge density is J, means the net amount of charge, that means the amount of charge, if the amount of charge is q and that one is flowing per unit time t, and also across the cross sectional area, a, then this can be defined as J equals to delta q divided by at. Is that clear? Is that clear, this formula? The electric current density J can be defined as J equals to delta Q divided by AT. Sorry, A delta T. Now, those who have, please bring your pen and paper and please try to write down these equations, which one will help you to understand from where we have derived this formula. Okay. Now, the next thing is that here delta Q is the net quantity of electric charge flowing through the area A in time delta T. Now look, electric current density will only happen when we will apply the electric field Ex. So if we apply an electric field E, if we apply an electric field in the direction of X, then that one will experience a force. So we know that force F, Coulombic force F equals to Q E, right? We know that force F equals to Coulombic force equals to QE, and we know that the flow of electron is the opposite direction of the flow of current. So if this charge is the negative, this one is an electron, so that one is the negative charge quantity. So that one will be F equals to E of X. Is that clear? Okay. Now, so let us assume that average velocity of an electron in the X direction at time t is denoted by Vdx. That means the average time, the average velocity of the electron in the direction of X. So say for example, I have n number of electrons. So the total average velocity, if we sum up all, if we take all the velocity and take the average of, that means if we divide those velocity with the number of electrons, then that one will give us the average velocity, and this velocity is known as drift velocity, or which one is sometimes known as instantaneous velocity, Vx. So the average velocity of the electron in the x direction at time t is denoted by Vdx, and this Vdx is known as drift velocity. So if in the exam, if I ask what is called drift velocity, I think all of you should answer these things. And there is another thing mentioned here, that the average velocity is something like 10 to the power. That means the average number of electron is almost 10 to the power 28 per meter cube. Okay. So I think up to the equation number 2.1, this one is clear. Now let us assume we have x number of electrons. Oh, sorry, we have n number of conduction electrons, and the in the x directions the last velocity is vxi. That means this one is the velocity, vxi is the velocity in the direction of x, and this one is the I electron. So suppose that n is the number of electrons per unit volume. So if the total number of electron is n, total number of electron is capital N, and small n is the number of electrons per unit volume, then n should be equals to, small n should be equals to n divided by v. Very simple. Now in time delta t, the electrons moves the distance delta x. So we know that displacement or distance s or x equals to vt. So delta x should be equals to v dx into delta t. So the total charge delta q crossing the area A. So the total charge delta q crossing the area A is ENA delta x. Okay, and this one is flowing in the direction of x. So we can write down, so previously I have told you to write down the equation, the current density jx should be equals to delta q divided by a delta t. Now if we put the value of delta q here, so delta q should be equals to e, so you can take delta q should be equals to ena ENA delta x. So we, if we replace this delta x, so delta x should be equals to VDX delta t. So look, delta x will cancel, cross sectional area will be cancelled. So what will left here? En VDX, isn't it? So the current density Jx should be equals to En VDX. Is that clear up to this? Now we know that usually, we know that usually we are present in a world where the two variable things, that one is the space variable and another one is the time variable. So most of the things are variable in terms of space and also in terms of time, as because we are considering that the electron or our system is flowing in the direction of x, but still now we have not considered with respect to time. So what we can write down, just simplify this equation, j x t equals to E n v dxt, because the charge of the electron E, the number of electrons per unit volume is n. So these two things are constant. So only the variable things is, that means the not variable with respect to time is v dxt. So I think up to this equation is also clear, up to equation number 2.2. Now, in this book, you will find they will explain the conduction of copper crystal in terms of in presence of an electric field Ex. So, so if you look at the figure 2.1, in the figure 2.1, then you will see that we are applying an electric field E of X, and that one is moving. That one will give the, that one will give this electron a velocity, drift velocity vdx, and the direction of the current density in the same direction of the applied force ex. but the direction of the electron is the opposite direction of the applied electric field. And you know that because the current direction of the current is opposite direction of the electron. Now they have explained these things in terms of copper ion. So this one is a face-centered cube, and the outermost shell is known as the conduction electrons. So you can go through these things, but this one is a very fundamental things. You can understand this thing easily. So what I will actually do, I will explain or I will show the derivation of these electrical conductions, that means the electric current density in terms of electric field or in terms of various parameters. Now look, if we look at this figure, figure 2.2, so if you look, there are numerous number of copper ions are there. And look, these no, there is no specific direction of this copper ion. So most of the copper ions are moving in its individual directions. So what I can say, so the two corresponding electrons are moving. So if we summarize the figure A, then we can find out the that means we can conclude with this figure to figure B. Look, so we are applying the electric field E of X, and that means we are just applying the voltage V. So the electron or the charge free or the free charges from these positions experiences a force, and that one will vibrate, that one will come here, after that that one will move, and gradually the final position is here. So this one is not the effect of a single electron, this one is the effect of various numbers of electrons here due to this applied electric field. And we are considering that this distance is delta x, that means the linear distance. Now let us assume that next things, that means if we consider the first electron, that means the first electron, the initial velocity is vx ux1, and the final velocity is vx1. Similarly for the second electron, vx2 and the ux2. So this one is in the vertical directions, they are mentioning the difference of the velocity, and in the x-axis or in the horizontal axis they are mentioning the displacement. So let us assume the first position is at t1 for the first electron, and it moves to these positions at the time t. Similarly for t2, moves to these directions at time t, and so on. Now we know that, so I think I need to share these things in the whiteboard. So we know that F equals to M A, right? And we also know that F equals to Q E, right? So we can also find out that, we can also find out this way: A equals to, sorry, A equals to Q E divided by M, isn't it? Now we know that what is called acceleration, that means V minus U, that means the final velocity minus the initial velocity divided by the time duration, that means t, that means the final time minus the initial time, equals to Q E divided by M. I think this one is a very fundamental things of physics, or the Newtonian physics. Now, if we look at the book, then we will find Vxi equals to Uxi plus E of x divided by Met minus Ti. So again look, so if this one is the Vxi, if we cross multiply these things, then what will happen? V minus U should be equals to Q E divided by M multiplied with T minus, that means Ti minus, sorry, Ta minus Ti. Now if you look, that one is, they are considering that the ith number of electrons, that means Vxi should be equals to, that means they took from the left side to the right side, Uxi and E of x, that means we have written that one is Q. So in place of Q we can write down the charge of electron E of x divided by Me multiplied with the time T minus Ti, as because this one is for the ith position or ith electron, so the time should be T minus Ti. Is that clear? Now similarly we know that, so Vdx, we know that Vdx equals to drift velocity or the average velocity of n number of electrons. So take all the velocity divided by the number of electrons. So this one is the velocity, isn't it? So this one is the velocity. So we also know that velocity divided by the time is the acceleration. So if we look, this one is the time. So if we divide these things here, then that one will give us the acceleration. So what is acceleration? Acceleration equals to E of x divided by Me. Is that clear? Now this T minus Ti bar is known as average free time for n number of electrons between the collision. And this T minus Ti bar is defined as tau, which one is known as mean time between the collisions. Which one is known as mean time between the two collisions. That means the average time between the collisions. Okay. So sometimes this one is also known as mean scattering time. So what might be the question come in your exam? So the question will be something like that. What is called mean time or mean scattering time, or define mean scattering time. Okay, then you have to write down from the average velocity. You have to define that T minus Ti bar, which one is known as mean average time. Sorry, average free time, or sometimes that one is known as mean scattering time. Okay. Now, so from this position, if we replace the T minus Ti bar in terms of tau, then we will find Vdx equals to E tau divided by Me multiplied with Ex. So up to this, is that clear? The average velocity or the drift velocity in terms of electric field. Now look, so in our case, this charge of the electron E, mass of the electron, and the mean scattering time, so these three terms is a constant terms. So we can write down these three terms in terms of a constant proportionality. That one is mu d. If we write down that one is mu d, so which one is also known as drift mobility? Which one is also known as drift mobility. So we can write down Vdx. We can write down Vdx equals to mu dex, where mu d should be equals to E tau divided by me. So in the exam, the question might comes like this: what do you mean by drift mobility or define drift mobility? Is that okay? Now look, this tau, this tau is also known as relaxation time. This tau is also known as relaxation time. So if we go to the, if what I have told you previously, please write down these equations in your notebook. So if we go to the electric current density J of x, so what was the last J of x? So if we go to the equation number 2.2, then you will find, so J of x equals to E n Vdx, right? Now E is a constant term, n is a constant term, and Vdx. Now we will put this value of Vdx there. So what is Vdx? So what is Vdx? So Vdx equals to mu dex. So J of x should be equals to En. This one is was same as previous, and Vdx equals to mu dex. Now look here, E is a constant term, N is a constant term, mu d is also a constant term. So what we can write down here, all these constant terms E, N, mu d with in terms of another constant proportional, that one is known as the conductivity, and that one is represented by Greek letter sigma. So J equals to sigma E of x. So the final equation will be, the final equation should be equals to J should be equals to sigma E of x, where sigma is known as electric conductivity. We also know that another terms rho, which one is called electric resistivity. So electric, the relationship between the electric resistivity and the electric conductivity is reciprocal or the opposite in relationship. Is that clear? And another most important thing is that previously we have learned about the relaxation time, and the reciprocal of this relaxation time tau, that means 1 divided by tau, is known as mean free of the collision or scattering event. That means the we know that the number of frequency per unit time, or the number of cycle per unit time, is known as frequency. So in the same way, the reciprocal of this relaxation time tau, the reciprocal of this relaxation time tau is known as mean frequency of the collision, and that one is also known as scattering event. Is that clear? Now they we know that Vdx equals to delta x divided by delta t, and they have said that the delta x, whenever delta t is greater than delta t, so you will learn these sort of things in your advanced level. So what you need to learn after this, the proof of J equals to sigma E. Now in the next one, so we'll find, we'll go to example number 2.1. So I will not solve in details of these problems. So what you have to do, you have to solve these things in your room. I will just give you some idea, and if you face the problem, then I will solve this math in the problem solving class. So look, the question in the example 2.1 is like this: probability of scattering per unit time and the mean free time. If 1 by tau is defined as the mean probability per unit time that an electron is scattered, show that the mean time between this collision is tau. Now the next example is example 2.2, electron drift mobility in metals. Now the question is calculate the drift mobility and the mean scattering time. Drift mobility means mu d. This one is the mu d. Next one is the mean scattering time. So mean scattering time means tau of an conduction electrons in copper at room temperature, given that the conductivity of the copper is 5.9 into 10 to the power 5 per ohm per centimeter, and the density of the copper is 8.96 gram per centimeter cube, and also the atomic mass of the copper ion is given 63.5 gram per mole. Okay, now you know all the formulas. Just just write down the formulas here. You will find out the mu d value. Very straightforward. Try to solve this thing. So in the exam, the similar type of question might come. So try to solve these things in your room. Otherwise, during the exam time, you cannot solve these things. Now the next one, example 2.3, the drift velocity and the mean speed. What is the applied electric field? That means you are asked to find out the E of x that will impose a drift velocity equals to 0.1% of the mean speed, and the mean speed value is also given 10 to the 6 meter per second of the conduction electrons in copper. What is the corresponding current density and the current through a copper wire of a diameter 1 millimeter? So you know all the parameters, you know all the values. So try to solve this thing. There is no equations or no formulas outside from this book or what I have covered up to now. So those who have the calculator, please solve. If you face any problem for solving these mathematical problems, then I will solve these things in the discussion class. Is that okay? Now go to the example number 2.4, the drift velocity in a field in a closed loop. You have to find, you have to also solve this example 2.4 by yourself. So now, so your first lecture will be up to the article number 2.1. The first lecture will be up to article number 2.1, and if you face any problem up to article number 2.1 or the at the very first lecture, then we can also discuss these things in our problem solving class. So now this will be the end of our first lecture, and in the next lecture we will start from article number 2.2. So thank you.